we are now in the Q&A section. So we got quite a few questions here. So let's just dive right in. The first one, I think, is something Kevin can address. Can you elaborate on microbump repair? How does redundant microbumps work?
So this is Kevin. On the HBM device is a JEDEC standard. So all the repair mechanism is really defined and agreed upon in JEDEC. For the microbump repair, you have several kinds of microbumps. You have the data or the DQ microbumps, and then you also have microbumps for the column and command, column and address. So each of those can be repaired using the IEEE 1500 protocol. And for the once you run the programmable BIST or the built-in self-stress test on the base die of the HBM bump and on the base die of the HBM, and you're able to identify where the failure location is, you can then use a DBI microbump to replace a failed DQ or a DWORD. And then you can use a redundant column or address microbump to replace the failed column or address microbump. So the HBM have several kinds of redundant microbumps, and for DQ, you basically use the DBI. If you use DBI to replace the DQ microbump, then you won't be able to use DBI mode.
Okay. All right, thanks. Okay, next one's a very specific question. How does pseudo-channel maximize the data transfers compared to legacy mode? So I think this might be one for, all right, Kevin's going to grab that?
I'll take that too. So with the pseudo-channel, what that allows is it's, since the pseudo-channel, you're able to share, actually the pseudo-channel has separate I/O, 64-bit I/O per pseudo-channel. So you're able to reduce the granularity of the memory access to each of the channel. What that does is that you're able to design your scheduler to effectively ping-ponging between the different pseudo-channels with smaller bits of data. So that allows you to fill up the data bus with more data and less bubble. So effectively, it allows you to maximize the transfer of data on the data bus.
Okay. All right, so the next question is, are the HBM and logic die grinded to ensure they are coplanar, or do you always use a lid? So that's an assembly question.
Yeah, so the HBM is received from SK at a known thickness, and the logic die is processed to match that HBM die thickness. So when the final assembly is completed, we try to ensure that the devices are coplanar, or at least within a range of the coplanarity.
Okay, thank you. So the next one is a question for Paul. Could you comment on the interposer areas on page 20? And there is page 20.
Let's see, that's page 20. So yeah, these are all color-coded. The green, of course, is the substrate. The silicon is the gray area here. And then the logic and memory devices are placed on top. I don't know if I have any specific thing that I can say about them other than the interposer, besides acting as the pass-through for the TSVs for signals coming up from the substrate, as well as interconnect between the dies. The interposer does act as a physical foundation for us to complete the assembly. So it's almost always oversized compared to the die underneath it. And that's important for our underfilling process to underfill the die to ensure high quality and high reliability.
Okay. Okay, next question. Are HBM2 stacks backward compatible with an HBM1 PHY?
I can take this one.
Okay.
So in theory, the answer would be yes. We have not looked at that situation in any great detail. That's not a usage model that we've really considered. What we see in the customer base is any customer who is using an HBM2 today, we're simply using our HBM2 PHY. and supporting them with the deliverables and the test chips that we're doing today. So in theory, yes, but in practicality, that's not what we're doing.
Okay. Next one is for Chris. Could you remind me of what with AP stands for in your command timing table? Again, very detailed questions. Thank you. This means everyone's really paying attention.
Okay, so can you just repeat that again?
Sure. What does with AP stand for in your command timing table?
Oh, well, just either auto pre-charge or you know, that's basically what it's talking to.
Okay. All right. Thank you. So this is a question for Kevin. What is the working temperature range for HBM?
Our data sheet specifies that the device operates at 85, 95, and also 105 is supportable. But in the higher temperature range at 105, there is limited support in terms of quality and reliability. I can't really speak a lot about that, but if you can contact me and make sure that we have an NDA in place, I can provide you a lot more details on the quality side of the HBM. But essentially, the HBM will support temperature range up to 105.
Okay. Thank you. And here's our final question, which I think is an interesting one to end on. Is there another memory provider in addition to SK hynix for HBM? If not, should that be a concern for customers? Supply chain question.
Yeah, so I can take this one. So yes, there's more than one supplier for HBM, and that is one of the benefits that we see in HBM in the industry as opposed to some of the competing memory solutions, is that this is multi-sourced. So this should not be a concern for anyone. There are multiple sources for the memory.
Okay. And one other question snuck in there, so we'll do that one, and then we will end. I want to be respectful of everyone's time. Can you comment on achieved performance for large bursts? For example, 4 KB data equal read and write.
Yeah, it seems like that would make sense for me to take.
Yeah.
So the answer to that is yes. If you have large bursts, you're going to get extremely good performance. Of course, it depends a little bit on the pattern of those bursts, but basically with large bursts, you're going to get close to the maximum possible bandwidth of the HBM device. If you have specific questions on that, please contact me, and we can provide a more specific answer based on particular patterns of those axes. But it should be very high performance.
Okay. All right. Thank you. Thank you, gentlemen, for the responses, and thank everyone in the audience for the great questions.